Organic chemistry is based on carbon-containing molecules with CH bonds. So some joke that organic chemists see the entire periodic table as carbon, except for a few other key elements. Now, this stereotype kind of makes sense. Organic chemistry arose as a discipline to describe the chemistry of life, and the elements contained within the human body are concentrated in this upper right portion of the periodic table. But if we're talking about biochemistry, there are other elements that are important as well. Trace elements in the human body include the transition metals. And many of the reactants that you'll meet in Organic Chemistry 1 and 2 span the entire periodic table. All that being said, I'm going to give in to stereotypes for a moment, and we're going to focus on the bonding of elements in the upper right-hand portion of the periodic table, because these are the most likely elements to be bonded to carbon in organic molecules. Let's briefly review the Octet Rule. Most elements like to have 8 electrons around them. This includes all of the electrons that are shared in bonds. There are many exceptions to this, of course, and a notable one is hydrogen, which only makes one bond and therefore has 2 electrons around itself. If you're not allowed to use a periodic table to complete your exam, it's wise to memorize the periodic table going over from carbon to fluorine and down the halogens. You can use my silly acronym, Can Normal Owls Fly, or come up with your own. Going from left to right, the number of valence electrons that the element prefers to have increases. And now we get to our little trick. Starting with carbon, we can count down from 4, and we get the number of bonds that the element likes to form when it is neutral. Now, phosphorus and sulfur also follow this rule, but they're special cases. Because they have empty d orbitals, they can actually exceed an octet of electrons around them. So phosphorus, when neutral, will form either 3 or 5 bonds, and sulfur can form 2, 4, or 6 bonds to other atoms when neutral. Let's look at a simple example of a molecule containing an element from each group, so we can correlate the number of valence electrons with the number of bonds that the element likes to make. Here I've drawn out methane with a pair of dots to represent the 2 electrons that are shared in the bond to hydrogen. In organic chemistry, it's more conventional to show the pair of electrons as a single line connecting the 2 atoms. Keep in mind that each of these lines is representing a pair of electrons. Now, to count valence electrons, we can think about splitting the bond in half and thinking carbon owns half of the electrons in each bond. Since carbon likes to have 4 valence electrons, carbon is neutral in methane. Now let's move on to ammonia, NH3. We see that nitrogen likes to make 3 bonds when it's neutral, and we have 3 bonds to hydrogen in the structure of ammonia. However, nitrogen likes to have 5 valence electrons, and we only have 3 coming from bonds. This is because nitrogen contains a lone pair. When an atom has a lone pair, you count the lone pair as belonging just to that atom itself, and so we have 5 valence electrons on nitrogen. We can look at the structure of water to explore the valence of oxygen. Oxygen is neutral when it makes 2 bonds, so bonded to these 2 hydrogen atoms, we have a neutral molecule of water. But its valence is 6. This is because oxygen has 2 lone pairs. So in water, oxygen is the owner of 4 electrons from lone pairs and half of the bonds to hydrogen. That's 6 valence electrons. For our fluorine example, we're going to look at hydrofluoric acid. This is a weak acid, but a really toxic molecule. Fluorine likes to make 1 bond when neutral, but it also likes to have 7 valence electrons. So fluorine gets 3 lone pairs. This gives it 6 electrons in lone pairs, plus 1 from the bond to hydrogen. This is 7 valence electrons. If we simplify our periodic table even more to remove the left and the right-hand groups, we can come up with a trick to figure out the formal charge on an element. The number of bonds the element likes to form when neutral is still written across the top of the table. Now, if the element is making 1 extra bond, it is going to be positively charged. And if it's making 1 less bond, it's going to be negatively charged. Let's look at water once again as our neutral example. Water wants to have 6 valence electrons, and it has 4 coming from the lone pair and 2 coming from bonds. The hydronium ion is a better way to represent H+, or a proton, in an acidic solution. Now, we have 3 bonds to oxygen, but we don't want to break the octet rule. We still only want to have 8 total electrons around our central element. So now oxygen has only 1 lone pair and a formal positive charge on oxygen. Okay, let's count our valence electrons to see how we figure this out. We already said we have 6 valence electrons in water. Now with the hydronium ion, we have 2 electrons coming from lone pairs. We also have 3 electrons coming from the 6 electrons that are shared in bonds. Remember, oxygen owns half of the electrons in the bond. If we add this up, we see that oxygen has 5 valence electrons total. Well, this is 1 less negative charge than the 6 valence electrons it likes to have when neutral. So if we have 1 less negative, 1 less electron, oxygen has a formal positive charge. All right, so we looked at an example where oxygen is making 3 bonds, 1 extra bond, and therefore has positive charge. Let's look at an example where it's making 1 less bond and has a formal negative charge. Hydroxide is a deprotonated form of water that exists in basic solutions. Let's count electrons. We have just 1 electron coming from the bond to hydrogen. Oxygen is only sharing electrons in 1 bond, so to complete its octet, we need to add 3 lone pairs. With the 1 electron from the shared bond and the 6 electrons from lone pairs, we get 7 valence electrons on oxygen. This is 1 more electron than oxygen likes to have when neutral. If we have 1 extra negative charge, we get a formal minus charge on oxygen. Let's return to our original piece of the periodic table for a moment that we were looking at. This formal charge trick works for all of the elements in the middle 3 groups. So it'll work for nitrogen and phosphorus, oxygen and sulfur, and the halogens. But it doesn't work for carbon. Let's see why. Carbon likes to have 4 groups around it. I'm going to label these groups R. This is a convention used in organic chemistry when we don't want to specifically define what the group is. Now, if we think about losing R but leaving its electrons behind on carbon, we get an extra lone pair on carbon. This gives carbon 5 valence electrons, therefore the atom carries a formal negative charge. Now, if we think about carbon ionizing by losing the R group with a pair of electrons, we get a different story. Carbon now has just 3 valence electrons. It wants to have 4, so it's missing 1 negative charge, and it takes on a formal positive charge itself. This species is called a carbocation, and it also has 3 bonds. So you can see why our formal charge trick doesn't quite work with carbon. In this lesson, we looked at the valence of atoms that are most likely to be bonded to carbon in organic molecules. We looked at some simple examples and figured out how to determine how many lone pairs are on each atom. We also looked at a trick for figuring out formal charge on the groups to the right of carbon and saw why this trick can't be applied to carbon itself. We'll look at the bonding of many more elements and practice Lewis structures in another lesson. KP here. If you learned something, give me a thumbs up on the way out, and for more chemistry, subscribe to my channel.